Is it okay if I explain or?
Yeah.
Okay, I'll share. Can you see?
Yep, we can see that.
Okay, so Tajna, you fill out this grid and then you fill it out in one direction and then you read it in another direction. And then you need to find the row by column, but it's a little bit confusing. It says rows and columns, but uh, it seems like it seems like um so you fill out the first example is uh bomb O so it seems like you fill out sideways 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 but it's kind of weird because that would it I think that seems more like the right side for me, so I got kind of confused at the start. Uh Generally when in programming, rows refer to the vertical rows, like rows refer to each horizontal row, the number of those horizontal rows, and then columns are vertical, and then the number of those vertical columns. But it seemed to be backwards from my intuition, but you can kind of interpret it. And then you want to fill out those rows horizontally and then read them vertically. But you don't necessarily have to create a new, you don't have to divide it into rows. So let's look at, I think it's like, oh man, let's try using, so one of the examples is Kowalski. And first you need to find how many rows and columns. So the number of, so n, which is equal to the string dot size, is equal to 6, right? And then you need to find factors of 6, which the smallest, the factor where r times c is equal to n and r is less than or equal to c, and r is the largest, becomes r rows equals 2, columns equals 3. Sorry. So if you read the problem, I think with some trial and error, you can get there, but one way to do it would be to go from every number from 2. You know, 1's always going to be a factor, so you can set 1 as the default value if n is the size, and then go up until n. If you and let the number of rows be I, and if number mod that number is 0, so if it's a factor, then rows is I, columns is n over I, and at a certain point you so let's say factors of 6, right? You get rows equals 2, columns equals 3, it multiplies to equal 6, and then at a certain point the rows become larger than the columns, so it becomes 3 times 2, and once you cross that point you can break and you've already gotten the answer. You can also do like maximum that fits this criteria and stuff like that. You don't have to do a break condition, but you should be able to figure out rows and columns like this. If you, I think, so Cole's code, it seems like you're trying to divide it out into different cases with like number of letters is equal to less than 4 and stuff like that, and number of letters. If you try to separate it into cases with different numbers of letters, I think you might get some weird issues. So if you can find a general case that fits everything by really reading the problem And looking at reading lines like this, you need to be really careful with and find something that works for everything. Unless it's like sometimes 0 is a special case, 1 is a special case, n is a special case or something. So those you might have to write specifically, but otherwise, I don't think you should really do stuff like less than 4, like try not to use hard-coded numbers that much. So I would stay away from that to try to minimize the number of bugs in your code. And then, so we have Kowaski rows 2, columns 3. I think with some trial and error, you'll get to this point. And I think it should be like, if you fill out stuff like this way, then it should be like ko, as, key, and then you read it this way, kak, OC. So what are you doing here? So if you apply numbers to this, then you have a 6-digit number, and then the index value, you can say this is the same thing as going 0, 1, 0, 1, 2, 3, 4, 5, and then you want to read it this way, So you want to go 0, 2, 4, 1, 3, 5. So how would you do this? So, well, this is column count, I guess, because, or wait, oops, 0. Oh, wait, I'm confusing myself. Do not write it like that. So you want to read it 0, 2, 4, 1, 3, 5, right? You want to read it like this. And then rows is equal to 2, columns is equal to 3. We established that before. And so how do you go 0, 2, 4, 1, 3, 5? Well, here to here, this is like +2, this is +2. Then it loops back. It goes to this number, and then you go +2 again, +2 again. So here it goes +2, +2. And if so you can, if you try a couple examples, so what if there's 0, 1, 2, 3, 4, 5, 6, 7, 8, and then you read this way and then this way, right? So this would be 0, 3, 6, 1, 4, 7, 2, 5, 8. Well, this is, the difference is always +3, but it divides into here, and then you do the +3 pattern 3 times, right? And when this number +3 is greater, this is greater than n, then you go to the next number and move forward, right? And so you can write this pattern as 0, and then you found out the row count. Row count is 2. So it's messy, but 0, 1, 2, 3, 4, 5. In the second sample, row count is equal to 2. And you'll see that you're doing this 2 times. If you're doing 0, 1, 2, 3, 4, 5, 6, 7, 8, you'll see that you're doing this pattern of going +3 times 3 times. So this is equal to the row count. So you need to figure that out. And then, so this index, we start at 0, and then the next number is +3, and then it's also equal to the number of items in this row. And this is somewhat calm. I think I've seen it in another problem before, but sometimes you have to kind of figure it out like that. And then that can be a way of doing it without extra space. Another thing you could probably do is create a vector, or I guess like an array list if you're in Java or something. Vector string of like of size row count, and then save like s dot substring of I guess, so the length of each one is gonna be this, which is 2, which is rows. I think, oops. So row, so it becomes more complicated, right? You'd have to like divide it out and create like an array of strings or something and create a 2D list and then read down this way. And that would be like for so you want to read up and down, up and down, up and down. So the inner thing, we want the we want to go like j goes from 0 to here or something, and then the outer thing we want to go this way. So if you just make sure to get the if it's a grid of ij, then this number, if you do I here, then you're going horizontally first. So I guess the j has to be, it's probably confusing, right? But you start to have create bugs. But so the outside should be j and the inside should be I if you're going vertical, vertical, vertical. Whereas in a regular for I for j, you'd be going like this, right? So if you filled out a 2D grid before, it's 0, and then if you have for I for j or something, then I of j increases like 0, 0, 0, 1, 0, 2, 0, 3, 1, 0, 1, 2, 1, 3, 1, 4, something like that. Whereas if you go for j for I and go grid of ij, then you go vertically. So you could kind of read it in, create like a 2D grid and then read for j for I, but it's definitely a lot simpler to go with the double, directly read it from the string instead of creating a secondary string. So Cole, what do you think? Was that confusing? Or...
No, that was very helpful.
Okay. Yeah. But I think the most confusing part for me was the distinction between rows and columns. Usually it's the other way around. So I'd be careful about that. But yeah, definitely write out the sample cases. And then even though you have these letters here, I think it's a lot easier to think about numbers. That might be kind of helpful. Think about like index numbers in this case. So I think writing out numbers would make a lot of sense for something like this. I'm gonna go to the next problem. And yeah, so I tried to update the hint thing. So if you yeah, if you do it the numbers and then adding +3 +3, if you find that pattern, you should be able to write it. So it's all about trying to find that. I don't know. I guess you can just keep on making new ones. What's another popular one? Trainboarding, video speed up, calculating dart scores. Dart scores is relatively simple, so let's do that. Anything like officers want to add? Any thoughts?
I think Jared explained that pretty well.
Yeah, it's pretty clear.
Calculating dart scores. Qualifying round, competitive round. Okay, so calculating dart scores. Has everyone seen a dartboard before? If you haven't seen a dartboard before, this problem might be a little bit confusing, but there's 60 total squares. So there's 20 inner, 20 here, and 20 here, and 20 here. But the total different scores that you can have are the double ring. So 1 to 20 or 0 to 20 if you don't throw, but 1 to 20 times 2 on the double ring, 1 to 20 on a single square, 1 to 20 on a triple, which triples your score, and then 1 to 20 on a single. So the number of different throws you can make in one throw, you can get either 1 to 20, 1 to 20 times 2, or 1 to 20 times 3. So let's say you throw 3 darts, or let's say you start with let's say you start with like dice, right? And you have like 3 die, and die go from 1 to 6, right? What are the different combinations of dice you can, or combination of things you can do? Well, first one you can do 1 to 6, so there's 6 options. Second one you can do 6 options, 1 to 6, 6 options. So if you visualize it that way, think about like coin flips or something. Well, the first coin you can have 2 options. The second coin you can have 2 options, heads or tails. Third thing you can have 2 options. So you can brute force all the options by doing a loop with all the options like 0 to 2, 0 to 2, 0 to 2, or something like that. And you can do the same thing with scores 1 to 20. But the scores are 1 to 20 times 1 times 1 to 3. And then you have 1 to 20 times 1 to 3, and 1 to 20 times 1 to 3. And you can actually iterate through all of these. So will this run in time? You have all these numbers, you can have 3 throws, and you have 1 total second, right? So if you calculate all of that, then 60, so 20 different options times 3, 60 times 60 times 60 is like 216,000, which is very, very small. It's very, very fast for a computer to do. And let's say you do score 0. If you miss a throw or you don't use up all 3 throws, then 21 times 3 would be like 63. And then you can do like 63 cubed, and that's like 250,000. So that's still within time. So all you have to do is for calculating dart scores, as long as you can, as you know that there's enough time, you can iterate on the multipliers and on the things. And if any of you have done like big O notation or algorithmic complexity, it might be really scary to have like 6 for loops here, but this is just 3 times. This is just like 21 times. So if you multiply everything out, it's not a lot of operations. And then try like multiplier times the first one, multiplier times the second one, plus multiplier times the third one. So what score did you get? And was it a single space? Was it a double space, or was it a triple space? And if adding all 3 scores up is equal to your target number, then you want to print out that number. And then here I have if I, which is if I is greater than 0, it's just a shorthand for that. So I is iterating on the score that you would get from your first throw. J would be iterating on the score you get from your second throw, and K is iterating on the score from the third throw. And if your I didn't miss, then you'd print out your first throw. If J didn't miss, you print out your second throw. And then I also did a fancy thing where I didn't want to do like a bunch of if statements. So I just created another helper function that prints out single, double, or triple, depending on what the multiplier is. So that just cleaned it up a little bit, not having like a bunch of if statements in here, but it's exactly the same thing. So yeah, that's all it is. So if you format it correctly, and if you understand that this is gonna be within time, then it's really easy. So you can actually do this with a lower algorithmic complexity. Let's say the Dart scores go from like 1 to 1,000 or something. And then if you, or like 10,000, let's say. So that's 10 to the 4, right? There's 4 zeros. And if you have 4 loops, then that can be like 10 to the 4 times 10 to the 4 times 10 to the 4, which is 10 to the 12. And this is not going to run in time. What we have here is like 60. So if you round 60 up to 100, it's like 10 to the 2 times 10 to the 2 times 10 to the 2, which is like 10 to the 6. So this is going to run very, very quickly. If it's like 10 to the 12, it's not going to run in time. So if it's something like this, then you can actually cut back and do 2 loops by doing, let's say your first throw is from 0 to 20, your second throw is from 0 to 20, and then we'll times 1 to 3 times 1 to 3. Then you can do your target score minus I times multiplier 1 minus J times multiplier 2, and you have this, let's call this multiplier 1, multiplier 2, right? So you have these 2 loops going, and then you have these 2 loops going, and then well, I guess it's 1 to like 10,000 or whatever. But if you do target minus this, then you have the score that you need to get with the third throw. And then let's say you have a number and you need to figure out whether or not you can get it with the Dart score. So you can try like, if you can divide it by 3, divided by 2, and it's equal to 0, and it's in range of the possible scores, or if you check that it's a factor of 2, and then it's in range, or if the number itself is in range of 1 to 10,000, and then you can actually find it in 2 loops and not have to iterate on the third one as well. So that's definitely something you should know about. Does that make sense? And if the number you have is divisible by 3, and the sorry, this is really messy, but target, so mod 3 equals 0, and target divided by 3 is in range. So something like that. Or divide by 2, it's divisible by 2, and the number divided by 2 is within the range of 1 to 10,000 or something like that. So if it's a valid score that you can get, so how you would calculate that for this Dart thing, where you can have 3 different multipliers, stuff like that, you might see that the target number is divisible by 3, divisible by 2, and see if it's a valid score or not. So yeah, I think the kind of complicated part might be the double score, triple score, but yeah, you can't just iterate on like 1 to 60, you have to multiply the scores by 2 or 3. That's maybe can be a little bit tricky, but I think if you figure out that you can brute force it and you get that. The rest is just formatting, stuff like that. So also just in the limit mod one, just in the limit. So by in the limit, so let's have an example. So let's say our target number, we have a random target number, and then we subtract the first row, right? We subtract the first row, subtract the row 2, and then we have target minus row 1 minus row 2. And then we have our new target value, right? And we need to figure out whether this target value is a valid score. So the possible multipliers that score, so that score, that new target is equal to either a score from 1 to 20, 10,000, and then that times either 1 to 3, right? So I'm trying to see if you can divide by 3, whether you can divide by 2, and then whether those numbers are within that range. That's all. Just in the limit. Yeah, so you have a number, you have a target value, you subtract the first row and the second row, and then what you're left, the new target value is that you need to figure out whether it's within range and times the multiplier. So that's one way to get rid of one factor, one loop. So that would run much faster. Okay, any thoughts, questions? Anyone solve it a different way? Or probably not for this problem, right? You just have to brute force it. Okay, let's talk about Trainboarding.
I can do that.
You want to do that?
Yeah.
Okay. I'll stop sharing. Or while you get set up, I can introduce the problem.
Sure.
Let me know when you're ready. So Trainboarding, you have people waiting at this platform, right? And you have people waiting from all along this platform. And then you have a train that pulls up, and the train has multiple cars, and each car is length L. So you have passengers at random points along this line, and you go to different train cars. And each car has a door at L/2, and within that. So if the train car is 0 to L, then you have a door here, you have a door here, you have a door here, and you have 3 different cars in this diagram. So the diagram helps quite a lot. Okay, I'll stop sharing. You ready?
Yeah. Okay, I'll explain the problem and how to solve it. Can you guys see my screen now? Can you guys see my screen?
Yeah.
All right, awesome. That's okay. I'm borrowing your code, right? Because your code is like super clean.
Okay.
Mine's nowhere near as clean as yours. So, okay. So basically, how do we solve this problem? I know, like, I'm not as good as at explaining the problem as Masaki, but here we go. So the first thing we're gonna do is we want to find like the number, like where the location is, right? So we read in NLP. So basically, it's the number of cards, the length of cards, and like the number of people. Yeah. So we use that number of people to create a loop here. So we start reading in location here. Then how do we find like the number of card that kind of the closest to the people? So we would do that by taking the location and divide it by the length of each car of the car, right? I think most of the problem that people usually face is the maximum and minimum cases. So Masaki here, he find the minimum of these two, because like if you take the location and you divide it by the length, and if like the location is very big, it's gonna kind of exceed
Can
when
you
you
show it on
divide
the diagram?
how do I do this? How do I wait? I mean,
Or on the right side, click on the pen thing.
pen thing. Right,
Yeah.
okay. Okay. Not
That
sure how
works
to
too.
use this thing. So basically, you have like three cars right here, right? So let's say it's like L equal 90. So let's say like the position, the location is variable x, right? I mean, if x is something like it's very big, like 1,000, right? And then when we take 1,000 and we divide by 90, we're gonna get something like 11 around there. You see that it's exceeded. Like that, there's not enough train to reach 11. So basically, if you don't include, you don't cannot exclude that, you're gonna be getting wrong answer, because obviously it's the n is only 3, so you cannot get anything more in there. Yeah, so basically here that's why he kind of take the minimum, and I think that's super smart. And then what do we do when we get like the number of card that mean the how do we say that, the position, um yeah, so when you get that number, you kind of make an array here, so you can count the passengers in, because we're gonna keep count that, so that because the problem also asks like for the maximum of passenger can be in one car, and that's what we're gonna do there. So here basically we find it the furthest the location from the passenger. So what we do is basically kind of create a distinct function right here, so we can find that. So what we do is that we take the location and we minus this by the car, the variable we just find, by dividing the location by the length of the car, and we plus it by L over 2. Why over 2? Because basically it say that the the door is at the middle of the car. So that's what we try to do here. And his maximum value here is to find like the maximum, like we take what we just find here and we compare it to the other results that we just found like on the previous loops, and we get the biggest value, and that is what we gonna kind of print output right here. And finally, what we're missing is the maximum number of passengers can be in one car. And how we gonna do that, we're gonna just find, we kind of search for the array here for the maximum value. Is that clear? Do you want to add
Yeah.
anything?
I guess it's useful to, what about when you have a choice of where to go? I think one thing you can do is think about different cases and just try them on top of the diagram. So let me,
Did you want to share a screen or something?
yeah, I'm gonna share screen.
Okay, I'll stop sharing.
So what I thought about was, yeah, there was a statement. So you have 0 to 3L, right? And let's say there's 3 cars or something. Let's say you have a value that's really close to L, but it's a little bit less. Then you can see kind of visually that this is going to go to the first car, right? And then you can see if it's to the right of L, then it should go to the second car. So it's, and then this where the car ends up, you can kind of guess that you have to divide by L, but what does that number get you? And let's say the value is around L over 2. If you do integer division, that's going to get you to 0. And then if you divide L by L, that's going to get you 1. And it just kind of happens to end up at the same. You need to check that case, but if you do integer division, then it'll kind of round to there. So as long as you're checking and you find out, if you figure out that location divided by L just gets you the 0 indexed car number, then it helps a lot. So I would just test out a bunch of points and like try dividing by L, and then try the minimum case and the maximum case and the L 2L. So 2L divided by L is 2, and then car number 0, car number 1, car number 2. And you should go to the second car, taking the higher number car in the case of a tie. So it kind of worked out, but you could do an if statement if it didn't work. And then if you're at 0, you should go to the 0th car. If you're past the last car, you should go to the n-1 car. So that's why there is the minimum of n-1 and L location divided by L. So n-1 is the last car, and then location divided by L is a number, and n-1 is the largest number that you can get if you're like way off at the edge of the station and the car just like goes past you. Yeah. Just tried to delete the comparison and it worked. Yeah, you might have been doing the opposite, right? Like going to the lower one or something. So yeah, location divide by L. Yeah, that kind of sucks, but yeah, can't understand why it works. Yeah. And then what about the did you get the distance to the car? So you have a location, right? And then let's say train car number 0. What's the distance of the door? It's L over 2 past this number, which is 0 or something. Train car number 1, it's L plus L over 2. So you can kind of figure it out by testing a couple points that it's car times L plus L over 2 is going to be the distance of the car of the door, and then the location minus that and taking the absolute value. So if you test a couple points, I think, and try to figure it out, it shouldn't be works. Yeah, and if you're at L, then you go to this point. Yeah. L, 2L, 3L, yeah. So minimum of location divided by L or n-1. N-1 is the highest value that you want. So if location divided by L becomes larger than n-1, you want to go to the farthest car, which is car number n-1. And I think for this problem, you didn't have to worry about so car, one thing to watch out for is, so car times L. So length of the car is less than 100. Number of cars is 100 or something, right? So 100 times 100 is, it's going to fit within the integer limit. So sometimes when you're doing multiplication, definitely double check that it'll fit within a 32-bit integer. If your location is 2L, so in that case, you have a choice between 2L over 2 or 2L plus L over 2. Each passenger waiting for the train walks to the door of the car which is closest to them, taking the higher number car in the case of a tie. So if you're at 2L, then each door is equal distance away, and you take the higher number car. L minus Yeah, 2L minus or 2L plus. I just sorted it into which car will you go to first, and then compared to that one distance. So if you're going to car number 2, then I just calculated it once. Distance to the car with the car value that I figured out the car number first, and then I figured out the distance once. So no comparisons. I didn't compare like the distance from this point to here, this point to here, take the minimum. I just figured out that location divided by L works first, and then found the distance afterwards. So that kind of simplified it, I think. But if you take the distances and then take the minimum, except for you should go to the larger one if they're equal, that can get a little bit more complicated, I think. But if you figure out which car to go to first, then you only have to calculate the distance once, which might be a little bit easier. Why do you have to compare like which train has more cars? You have to compare which train has more cars. Which train has more passengers? At the end, you can just run through. So there's a passenger count. So I'm keeping track of n different train cars and then start at 0. And if the passenger is going to that train car, increment it. And then at the end, I'm using max element, but you can just do like a for loop for every int in like passengers, and then like max passengers is equal to max of max passengers, comma I, or something like that. And this is the exact same thing as this line right here. But you shouldn't need any comparison. Yeah, this would be a comparison, I guess. This is like the same thing is if I is greater than max passengers is equal to I or something. But you can rewrite it as this in a for loop, and you can rewrite that as this. If you do like competitive programming stuff, you figure out like what is viewer lines, and it doesn't really matter. Maybe max element is more readable, maybe it's less readable, but compare which train has more cars. But the passenger doesn't go to the car with fewer passengers. It just goes to the higher number car, even if there are a lot less people in the lower number car. So you don't have to do any comparisons. So that might be something there as well. Okay, do you want to move on to the next problem? Go video speed up. Video speed up, I thought was kind of tricky. So you have a video. Is it okay if I move on, by the way? I have to check people. Yeah, you don't need to check people. So make sure to read the problem, and you don't, intuitively, you should go to the car which has less people if they're the same length, the same amount of distance away, right? You'd probably, if you're a passenger there, you'd probably go to the one with less people, but assume that X prime is the same as the original video, except certain segments of the new video play faster X, but every time Y happens, speed it up by Z. So what's the hint? So from timestamp 0, from time 0 to timestamp 0, these are not the same thing. The video will move at regular speed. Maybe show diagram. So you have your video, right? And then at certain points in time, so when X happens, a plus certain percent, right? And it goes faster, plus something percent. So it gets faster and faster. But from time 0 to timestamp 1, this is going to be at regular speed. So that's maybe one thing you should think about first. And then let's say from time X to X plus 1, you're going at like 200% speed. So for, let's say you're at 5, let's say you play a video for 5 seconds and it's playing at like 2x speed. Well, in the real video, like 10 seconds have passed, right? And you can kind of, if you try a couple combinations, you can find out that it's the difference in time times the speed is the time passed in the real video at each thing. So from time 0 to timestamp 1, the speed is 100% or 1, and then it goes to like 120, 140, 160 and stuff like that. It doesn't scale like 120, like it's not like 120 times 120%, you know? It doesn't go like 1.2 times 1.2, which might be like 1.44, right? So it doesn't do that. It just does it, the percent is additive. So that's another important part as well. So if you figure that part, so really important thing is to try to think of the cases. If you have a number line here, it can be pretty simple to figure out, like let's say you're playing a video at 2 times speed for 5 seconds, then should 10 seconds might have passed in the original video, things like that. If you can kind of think about it that way, then you can try to, so now you can add up each segment, and then that's going to equal the original length of time that it took. So answer first equals time of 0, because the time of 0 to, I should rename this to timestamp of 0. So at timestamp of 0, up until timestamp of 0, you're moving at regular speed. So you can just add timestamp of 0. And then for every next one, find the difference in time between the previous timestamp and the next timestamp. So the time like from here to here, for example, and then times it by the speed. And the speed formula is given here. So 100 plus like I times P. And if you like look at the sample cases and try a couple numbers out, you should figure out that it's like P times I, with I being like 0 indexed timestamp numbers, but you can kind of mess with this if you do it a different way. But this kind of makes it easy. And then answer plus equals the difference in time times the speed that you do it, add up everything at the very end. So at the very end, you have a time between, there's the last timestamp right here, and then there's the time where you end right here. So make sure that you're taking the K, which is the final time, minus the last timestamp, and then multiply it by the final speed. Make sure you're doing that last part as well. That's all you need to do. And then you have to output a floating point number. So that is different with every language, but yeah. And so if you have a bunch of zeros afterwards, it's completely fine. It just matters if the relative error is small enough. So you can output more numbers than necessary. Anyone have any questions with video speed up? I think if you draw a number line, then it kind of helps. And if you figure out that it's additive, they give you the formula, right? But if you, I thought it was like multiplicative. Like sometimes speed up is like multiplicative, but the speed up is additive. So that's important to think about. And then maybe think of like real life numbers. Like it's kind of hard to say like timestamp 1, timestamp 2, and then the difference between them. You have the speed. What is it? If you think about it, like if 5 seconds have passed and it's at 2 times speed, then 10 seconds in the video have passed, right? Like something like that. If you can put numbers to it, that can make it a lot easier. Same thing with like other questions. If you can like plug in actual numbers into parts of it and figure it out, then it helps quite a lot. So for every speed, like plug in some numbers for P and some numbers for I, and just try to see that you're getting the right numbers at every step. I think I've deleted them, but usually I have like C out, speed, and line and stuff in my code, right? While I'm debugging, and then I comment it out, stuff like that. So that's a good habit to do. Like before you submit, just like check your speed, check is everything working correctly, and then you can figure out a lot of mistakes through that. So then the last one is going to be Baloni. I think that one Jesse solves as well. So do you want to talk about that?
Actually, I gotta head out for another meeting right now.
Okay.
Yeah, so I'm gonna make you the host, and yeah, it's up to you if you wanna keep going with this problem because it's already 5:30.
Okay.
Yeah,
We'll just
completely up
talk
to
about
you.
this problem. Yeah, this problem is kind of difficult in comparison to other ones. So you have a bunch of balloons. So you have a bunch of balloons, right? And you shoot an arrow, and when it hits a target, it goes down a level, and then you need to find the next target. And then if it pops it, then it goes down a level again. So whenever you pop a balloon, an n squared, so if you use big O notation, an n squared solution would be like find, let's say this is height I or something. Find h of I minus 1, right? And then if you find h of I minus 1, it's like find this h of I minus 1 again, and then mark it as used or something. But every time you, like for every index, you check every index. And then this is clearly n squared, right? You're going through the array one time and you're going once every time. So this becomes an n squared thing. So what can you do? So you have a bunch of these balloons, stuff like that. Well, if there's none below, then you're always going to add 1. But if there's one above it, you kind of get this one for free, right? You shoot this one and then this one becomes shot. So you can add 1 here if there's none below it. But for the second lowest one, if there's one at height minus 1, you can get that one for free, basically. But and then afterwards, you get one thing at plus 1 from here, plus 1, height plus 1, you get another free one. And if there's one at height plus 1 from here, this one becomes free as well or something, or maybe it's this one. But so you can, a couple ways to do this, but so let's say the last one is like h of I or something. Then going from I is equal to n minus 1 to 0, you can say store h of I plus 1 or something. And then if you find that, if it's the balloon on the, if you find that, if you go backwards and find a one at a higher level, then again, you can get rid of that and then say store h of I plus 1 again. Another way to do it is like grow from I equals 0 to n, and then go, you have your balloon at h of I, and like store h of I minus 1 in, and keep account of that. And later, when you find h of I minus 1, you can subtract that and store minus 1 again and keep on going. And at the end, you can add up all the numbers in that array. So, or so you need to like, you need to store the heights that, but you need to store the target heights that you're looking for. It's a little bit annoying. I think, anyone having questions? This? So there's two ways to do this. You can store the numbers in either, you can have a really large array and then store like 1 or 0 and stuff. And then this is the height at I. For every height or something, no. For every height value, you can kind of store. So if you find like, if you need, if you need h of I minus 1, you would store h of I minus 1. And then when you find it, you minus 1 and then add 1 here. And then this becomes 2 and stuff like that. So it'll be clear when we look at the code. Yeah. So let me find it. It's called again, Baloni. Okay. Yeah. So I have a map, which is pretty much the same thing as a really, really large array. And so if you think about an array of size like 10,000 or something, and then it's storing like a count. And instead of doing that, you can have a map instead. Really important thing with map that I really should mention is that hash maps in C++, this is kind of tangent, but hash maps in C++ are actually pretty bad for, is there ordered map? Yeah, ordered map is a tree map. So if you use a regular map, then it's actually a tree map. So it's stored in order, whereas unordered map, it's in like random locations because you hash the number and you store it in random places. So you get in a random order. Whereas in a map, it's a tree. So it's like a balanced binary tree. So it's stored in order. It's more efficient. I think space efficiency, unordered map, it takes up more space, and then map takes up less space, I think. And then time complexity wise, inserting into an unordered map is constant time, and inserting into a regular map is log of n. Can it be used for Java? Yeah, Java is Java, yes. Java, you either use tree map or you use hash map. Like hash map or tree map. And then, so basically you have a number. So int just means you have your key, and then you have your value. So you have key value pairs. And you can store a number like, let's say m of I minus 1 plus plus. So what I'm doing is storing at the value map of I minus 1. I minus 1 is the key, and then the value might be like 1 or something. And the default value is 0. So adding will do that. But if it goes back down to 0, it doesn't erase it. So you sometimes have to manually erase it and stuff like that. Is map in Python ordered or unordered? I don't know. I don't know about Python. But yeah, basically it's like having a really large array, except yeah, arrays are always going to be faster, but sometimes you just can't make a really big array. So I think arrays larger than like, what was the max value here? This is 1 million. 1 million. 1 million is like kind of pushing it, but I guess you can make an array of size 10 to the 6, but 10 to the 7, I think that's kind of pushing it as well. 10 to the 7, maybe you can make an array of size length 10 to the 7, but yeah, if you have a wide range in heights and you need to store a bunch of like different values, then using a map might be better. And I think like a lot of posers, their favorite data structure is the hash map. Not to should talk people, but a lot of people like hash maps. So basically you use like a hash function, which means you convert whatever you have and convert that data into a new hash key, and that's consistent. And then you go to the memory address that that hash creates and stuff like that. And so hashing it is generally, so I mentioned like unordered hash map in C++ is pretty bad. So if you're doing like a coding competition like Code Forces, you actually have to use like custom hashes, custom hash functions. And like I have this one saved here. And then, so this takes a random value based on the system clock. And then you do like, this is XOR with the number, and then you shift it XOR with the number right shifted 16. So yeah, but I don't get how it works, but basically chrono, if you get the current clock time, you get like a really large number, but it's like a pseudo random number that's really large. So people can't like hack your solution. And then you use like XOR, stuff like that. So people have like come up with different ways of hashing and stuff like that. But if you just use the standard, so the way you do this is go unordered map int custom hash, and then it just works. But if you don't do that, then when you have a bunch of values above 10 to the power of 9, then sometimes it'll map to the exact same value, because they hash using a 32-bit integer. It's really, really dumb, but if you have numbers above like 10 to the 9, then it'll hash the same value. So what a hash map does, I know I'm like getting into tangent here. I don't know where my pen is. So you have a number, right? Number, and then you hash it. And then once you get the hash code, you get a hash code that goes to a different memory address. And then different hash codes might go to different memory addresses. But if the number is like over 10 to the 9, then it'll go to the same memory address, and then that's called a collision. And when you have a collision, it makes it into a linked list, which is pretty slow. So all you need to know is like the hash function is bad and the default C++. But yeah, so it can create collisions. Yeah, so if you, but regular map is a tree map, so you don't have that issue and you don't have to have a hash function. Why didn't they use 64-bit? I don't know. Like, why do you have to write out long every time instead of using long, right? Like long is a 32-bit integer. Int is a 32-bit integer, depending on the compiler. And it's like so stupid, depending on like the architecture of your computer or something. So you have to use like long instead of long, and long is like effectively useless. So yeah, C++ has like a couple of those things. I don't know too much about like the ins and outs of like stuff, but yeah, I think in other languages, I don't quite remember about Java, but I'm pretty sure you can just use long in like every other language, and it'll be a 64-bit integer, stuff like that. So yeah. Yeah. But yeah. But I guess the good thing is like C++ is like less, you can write less, and it doesn't do stuff like, you can mess with memory addresses and stuff with C++. So if you go out of bounds of a array or something, it doesn't give you a warning, stuff like that. It's like good and bad, I guess. And like true is equal to 1 and false is equal to 0, which means like you can use it in a conditional. So if you do like Java, you have to do like equals true every time. Whereas in C++, you can just have it within the conditional, like if 1 will like work and if 0 will like be false or something. And if you have like a conditional statement, if x, and if x is like 0, then it'll be false. Like non-zero, including negative, then it'll be true. So like -1 is true. So sometimes if you're skipping values, then using a number as a conditional is like kind of bad. So it's like another thing, if you do like while x and you skip over 0, then sometimes you get infinite loops and stuff. But you can just do like while x is greater than 0 or something. So there are ways around it, and you have to be careful, but you can also like write stuff in a shorter way sometimes, and it's kind of cool. That's the spiel about maps, stuff like that. So a tree map is you have a binary tree, and then at every index, you have a balanced binary tree, and then at every index, that might contain multiple values. You have the index value, and then or you have the key value, and it's sorted by key value. You have a binary tree sorted by key values, and then you have the key plus value in the thing. So if you try to find the value, it'll take O of n. You'll have to look through the entire tree. But if you look for the key, it'll take O of log n, because the height of a balanced binary tree is log n. Because yeah, because let's say you have like n numbers, then when you go down, when your lowest value, let's say you have n numbers here, then you have n over 2 numbers here, and then you have n over 4 numbers here. So the height of a tree is going to be log base 2 of n. Yeah. So whenever you store a key, so when you like add to a tree, it's log n. And then if you find key in tree, it's log n. And then if you add to like a hash map or something, then that's order of 1, but you're using a hash function, which is like a slightly slower order of 1. And then when you find it, you get that value, you hash it, and then you try to find that value. So again, this takes order of 1 as well. So if you have like large values, it can make a difference, but logarithmic is like, if you think about logarithms, like log base 2 of like 100, and then log base 2 of like 1,000, it's like not much different. Even if you have a log base 2 of like 10 to the 9 and stuff, it's like really not that much. Let me Google it actually. Log base 2, and then 1, 2, 3, 4, 5, 6, 7, 8, 9. And then you get like 30. So this is like equal to 30, which is insane, right? So somewhere it's like a constant factor almost. So logarithms are, yeah, logarithms are good. When in doubt, calculate it, and you'll see that it's not a big deal. So yeah, it's maps versus hash maps. But I don't think you'll need hash map for anything. You can just use map for everything, and it should work for most things, because it's just a logarithmic time complexity difference. And then hash maps can have collisions. So those two things. Yeah. So the issue with the collision is like you hash it to the same place, but you need to store 2 different keys to the same hashed location or something. But we need these maps and stuff. Yeah, for sure. I think probably do a data structures thing. I don't know, maybe even next week or something. Yeah, we'll have a presentation instead of a scuffed thing. We can do this. Yeah. So this is a preview for next time, I guess. I think the only time I've seen trees is like for tree maps. I honestly like a lot of graph problems seem like trees, but you just get like adjacency lists. So it's not even, it's like a 2D array anyway. So it's kind of weird. I think, yeah. Okay, I have to go now. Cool. So hopefully that was helpful, and yeah, we'll go over data structure stuff. We'll, yeah. Thanks. Stop recording.